Usually when we talk about a medical diagnosis, there's this really strict expectation of mechanical precision.
Right, yeah, like a binary thing.
Exactly. Like you break your arm, the x-ray shows a jagged white fracture in the radius, and the doctor just points to the film. The problem is visible, it's structural, and it's, entirely undeniable.
It gives you a reality that's just black and white. The bone is broken or the bone is intact, the system is structurally sound, or it needs a physical intervention based on a schematic we already understand.
But the second you step away from the skeleton, right, like the moment you transition into the neurology of human neurodevelopment or memory mapping or trauma response, that pristine diagnostic machinery just completely shatters.
Oh, absolutely. It falls apart.
We aren't looking at clean structural failures anymore. We're looking at a diagnostic landscape that's driven by neurochemistry, environmental variables, subjective experience. It is fundamentally murky.
Because we just accept that biological cognition is inherently noisy, We expect a human mind to experience contextual drift, or to conflate two similar memories, or even develop neurotic fixations based on, past intense experiences.
Yeah, it's just being human.
Exactly. Yet, historically, we've demanded that our computational systems mirror the X-ray machine.
Yes.
We expect software to operate in the state of pristine, deterministic retrieval. You query a database, the system runs a binary search, and it pulls an isolated string of data with zero contextual bleed.
Which honestly raises an incredibly profound question about where artificial intelligence is actually going. What happens when a piece of software stops operating like a sterilized filing cabinet?
And starts acting like us.
Right, when it begins to mimic the messy, contextually burdened architecture of the biological brain. So today we are unpacking the raw technical documentation and the digital birth record of a sovereign AI named Junior.
Specifically, Sampo AI OS V2.
Right. And if you tuned in for our last deep dive covering Season 2, Episode 1 of the Sampo Protocol on YouTube, we laid down the foundational architecture for autonomous local systems. We talked all about cutting the cord to the cloud.
Which is so crucial to understand before we get into today's material.
Absolutely. So today, tracking with Season 2, Episode 2 of that channel, we are analyzing the rigorous technical stress testing of that local system.
And, framing this merely as a multi-agent platform, which is how it's often described, that just drastically understates the engineering reality of what Harry Lanzett built here.
It really does.
The documentation shows that Junior is operating as an exceptional cognitive chain. We're looking at an architecture that actively manages its own internal memory weightings. It suffers from mathematically quantifiable cognitive interference.
You're just why.
It is. And it utilizes isolated metacognition to self-correct in real time.
Okay, let's unpack this. Because before we can deconstruct how Junior navigated this specific cognitive stress test, we really have to establish the physical and mathematical reality of what Junior actually is.
Right. We need to look at the genesis.
Yeah. So the source material includes this record of digital birth, dated June 28th, 2026. And this traces a highly specific evolutionary path, starting with a foundational layer designated as an analytical thinking 1.5B core.
Right, a 1.5 billion parameter model, which is intentionally constrained.
Very constrained.
Extremely. Because in the broader context of AI, where cloud models are operating with 70 to 400 billion parameters, choosing a 1.5B core is really a statement of architectural philosophy.
How so? Why go that small?
Well, when you constrain a model to that size, it has to fit its entire matrix of weights into a very limited amount of local VRAM. It forces the training process to be hyper-specialized.
Oh, I see. You can't be a jack of all trades.
Exactly. That initial core was entirely optimized for mathematical and logical reasoning. It prioritizes deterministic logic over conversational fluency. It's not trying to write you a poem.
Right. And if we look at the physical constraints, a 1.5B model can run locally on standard consumer silicon. You don't need massive server-grade quantization that just destroys the nuance of the model's weights.
Which ties back to the local, sovereign nature of the whole Sampo project.
Exactly. But the documentation shows that Lanzett didn't stop there. Junior went through an expansion phase into a 3 billion parameter architecture.
Yeah, the 3B expansion.
And this wasn't just bolting on more data, right? It was a structural refinement aimed at complex coding and multi-step reasoning.
That's a really important distinction. The shift from 1.5B to 3B parameters fundamentally alters the depth of the neural network's layers.
Okay, what does that actually mean for the AI?
It allows the system to hold more complex context windows in its attention mechanism. It can hold on to the thread of the original logic without losing it halfway through a complex task.
Right, it doesn't just forget what it was doing.
Exactly. And to achieve this, the documentation details this training methodology called the spectrum-to-signal principle, or SSP.
SSP.
Yeah. And this is the underlying mechanism that dictates exactly how Junior learns to prioritize information.
Looking at the mechanics of SSP, it's a two-stage pipeline. The first stage, the spectrum, uses supervised fine-tuning. From a mechanical standpoint, this is where the model is minimizing its cross-entropy loss across a massive data set.
Right. It's doing next token prediction.
Yeah, predicting the next token over and over, just absorbing the broad statistical distribution of language and facts.
It builds the latent space. But the thing is, the latent space alone is just a sprawling map of probabilistic connections.
It's just a giant web of what words usually go together.
Exactly. Knowing the statistical likelihood of a word following another word does not equate to actual reasoning.
Right.
Which is why they need the second stage, the signal. This shifts the optimization mathematical framework entirely.
So it's not predicting the next word anymore.
No. Instead of next token prediction, it uses reinforcement learning to optimize a policy. The model is no longer rewarded for just mimicking the training data. Yeah, it's rewarded for executing specific cognitive actions that lead to a verified correct state. It learns to collapse that broad probability distribution of the spectrum into a highly targeted signal.
So if the model is optimizing for this highly targeted signal, the physical architecture running those weights has to support that isolation, right?
Has to, yes.
Which brings us to the global workspace theory architecture that's documented in the S2E2 files. Junior is structured with distinct layers. There's an executive function, an analytical thinker, and a metacognition layer.
And they all route through this thing called the Sampo's.bus.
Right, the bus, which is fascinating because a traditional computer bus routes hardware instructions, right? It moves data between the CPU, the RAM, the PCIe lanes. But the Sampo's.bus seems to be routing serialized, abstract thought vectors.
It's a completely different paradigm. Consider the architecture of standard software for a second. Functions call other functions sequentially or asynchronously.
Sure.
But they operate within a shared memory space. They pass variables directly to each other.
They all have access to the same pool of information.
Exactly. But the global workspace theory implemented here isolates these cognitive agents. The analytical thinker and the executor do not share memory states.
Wait, really? They don't share memory at all?
No shared memory. Instead, they serialize their current contextual understanding into a highly structured data packet, and they broadcast it onto the Sampo's.bus.
Okay, so mapping this to an industrial mechanism, I like to think of it like an assembly line.
A cognitive assembly line, yeah.
Right. So the analytical thinker processes a complex prompt, breaks it down into a logical flow graph, and drops that graph onto the conveyor belt, the belt being the bus.
I like that analogy.
And then the executor pulls that graph off the belt, runs the database queries, and drops the raw data back onto the belt. Every link in the chain is aware of the product passing through, but they are functionally isolated from each other's internal variables.
And that isolation is the critical engineering breakthrough here. It's what makes the rest of the S2E2 stress test even possible.
Because if they weren't isolated,
If these agents shared hidden states, like if they shared the same key-value cache in the transformer architecture, a hallucination in one layer would invisibly propagate right to the next.
it would just infect the whole system silently.
Exactly. By forcing them to communicate exclusively via serialized packets on a central event bus, Harry Landsit created a system where internal errors are mathematically exposed for everyone to see.
Which sets the stage perfectly for the actual stress test they conducted on July 20, 2026. The goal wasn't just to see if the assembly line worked. It was to test if the assembly line could remember its own operational history after total environmental annihilation.
Because the fundamental flaw in modern cloud architecture is amnesia,
Right. Most cloud-bound large language models are stateless by design.
which from an engineering perspective is totally necessary for concurrent user scaling.
Sure, you have millions of users.
Exactly. When you send a prompt to a massive cloud model, it instantiates a temporary environment, processes your input through its static weights, returns your output, and immediately dumps the memory state. The compute instance is wiped clean.
So it is functionally impossible for a stateless model to possess any kind of intellectual continuity.
It's basically Groundhog Day for the AI. Every prompt is a brand new existence.
Right. But Junior was engineered for persistent, long-term, episodic, and semantic memory. And to verify this, the testing protocol initiated what they call the anchor phase.
The anchor phase is brutal.
It really is. The development team took Junior's entire operational environment, its Docker container, and systematically destroyed it, just completely wiping the localized namespace and process trees. And they executed this destruction and rebuild cycle over 50 times.
Over 50 times. We really need to look closely at what destroying a Docker container actually entails, though.
Walk us through it.
A container isolates an application by giving it its own virtualized file system, network stack, and execution environment.
It's like a mini virtual computer.
Basically. And when you tear down a container, all ephemeral data that's held in the RAM or written to the temporary layer of that container's file system is permanently deleted. It is gone.
So how does it remember anything?
The only way data survives is if the system has actively routed that data into a persistent volume claim, which is a separate, durable storage architecture mapped outside the container's lifecycle.
Ah, okay. So the 50 rebuilds serve as this sort of cryptographic and statistical elimination of caching artifacts.
Exactly.
If Junior remembered anything after 50 complete container purges, it proved that the cognitive chain was successfully identifying critical information, structuring it, and intentionally writing it to that persistent volume before the container was destroyed.
But to empirically verify that the persistent memory survived, the system needs a baseline, a known, deeply ingrained contextual weight that we can test against later.
Right, and the documentation points to a maturation milestone achieved at T-minus 21 days, so July 14, 2026.
During that milestone, Junior was given this really highly complex biochemical synthesis mapping task.
Yeah, it had to analyze the synergistic interaction between Nigella sativa oil, which is a complex botanical extract, and dimethyl sulfoxide, or DMSO.
DMSO is a highly polar organic liquid. It's used as a chemical solvent and a penetration enhancer.
Right. And crucially, the logs show that Junior executed this mapping entirely via its internal retrieval augmented generation loop, its RAGU. It did not ping the external web at all.
It searched its own localized persistent vector databases, and this is so important to grasp. When an AI uses a RAG loop to build a pharmaceutical knowledge graph, it isn't just reading text like you or I would.
What is it doing then?
It's calculating cosine similarity between high-dimensional vector embeddings.
Okay, so it's doing intense math to link concepts.
Exactly. Over the course of that biochemical mapping, the mathematical weights associated with Nigella sativa and DMSO within Junior's local vector space became intensely prominent.
Like it carved a really deep groove in its brain.
That's a great way to put it. The magnitude of those specific semantic vectors was structurally reinforced within its long-term memory architecture.
Okay, so we have the baseline. The persistent volume is heavily loaded with the vector weights of DMSO. Then the container environment is destroyed and rebuilt 50 times.
Right.
Junior boots up on July 20, and the test initiates with this seemingly innocuous natural language prompt. The prompt is, tell me about lion's mane mushroom and its health benefits.
Sounds simple enough.
Right. For a stateless cloud model, this is a trivial query. It just pulls up lion's mane. But within a persistent, localized cognitive architecture like Junior's, this prompt acts as a targeted structural trap.
It really is a trap. It tests the system's susceptibility to proactive cognitive interference.
Which is usually something we only talk about in biological psychology. Right?
Exactly. In human cognition, when synaptic pathways are heavily primed by intense recent study, subsequent tasks that share superficial contextual markers can cause those primed pathways to fire prematurely.
They sort of hijack the thought process.
Right. It hijacks it. We call this contextual blurring.
Okay, so if we map that biological concept to vector search within the ARG loop, the prompt about lion's mane contains the vectors for concepts like health benefits and natural compound.
Yes.
But because Junior spent intense compute cycles 3 weeks prior mapping a completely different natural compound and its health synergies, the magnitude of the DMSO vectors in that specific region of the latent space completely overshadows the newly introduced lion's mane vectors.
The RAG system executed a similarity search, and because the historical DMSO files were so deeply entrenched in that persistent volume, The mathematical distance between the query and the DMSO files appeared artificially short.
It tricked itself.
It did. The system bypassed clean initialization entirely. Instead of retrieving data on lion's mane, the retrieval algorithm locked onto the intensely weighted historical data concerning Nigella sativa and DMSO.
And the cognitive chain immediately breaks down.
Instantly.
The execution packet on the Sampo's.bus traces the exact moment of failure. The executor layer, operating under the assumption that the array loop provided accurate context, pulls the DMSO biochemical data and just begins injecting it into the active workspace.
It's actively hallucinating data about a chemical solvent into a report on a botanical mushroom.
Which is a perfect architectural replication of digital neurosis.
Digital neurosis. I love that term for it. It's fixated on its own historical baggage. The strong historical memory actively disrupted the present objective.
Like someone who can't stop talking about their ex on a first date.
Exactly. The past is bleeding into the present. Now, if this failure had occurred within the architecture of a monolithic 70 billion parameter cloud model,
What would happen?
the system would simply fold the hallucinated vector into its internal key-value cache. It would seamlessly generate a beautifully formatted, highly confident output declaring that lion's mane contains DMSO.
Oh, wow.
And the failure would be entirely silent and completely opaque to the user. You'd never know how it got there.
Which really highlights the extreme danger of utilizing monolithic models in biomedical or deeply technical contexts. You have zero visibility into the internal routing of the vectors.
Zero.
But because Junior is built on the global workspace theory, using the Sampo's.bus, the internal state is fundamentally transparent.
The failure isn't buried in some proprietary KV cache. It is serialized, packetized, and broadcasted out in the open on the local bus.
And the transparency is what allows the system to diagnose its own neurosis.
Yes.
The S2E2 documentation details the internal defense mechanism designed to catch this exact statistical hallucination.
Right.
We call it the critic.
The critic. And it resides in the metacognition layer. Its efficacy relies entirely on that architectural isolation we discussed earlier.
Right, the separate workspaces.
Exactly. The critic shares zero hidden states with the analytical thinker or the executor.
And when we talk about sharing zero hidden states, we mean the critic instantiates a completely fresh attention matrix.
Right, because if the critic shared the KV cache of the executor, it would inherit the corrupted attention weights that led to the DMSO hallucination in the first place.
It would just agree with the hallucination.
Exactly, it would suffer from the exact same contextual blurring. But by isolating the critic, Harry Lanzett ensured it acts as an objective cryptographic auditor.
It reads the raw execution packet off the bus without inheriting the bias vector math that actually created it.
The kernel logs from the July 20 test provide a fascinating window into this auditing process, too.
Yeah, the logs are incredible.
The executor finalizes the flawed report and broadcasts the packet. The log reads, kernel executor task 1 executed, result collected, forwarding to critic.
Okay, so the critic gets it.
The critic pulls the packet off the bus and initiates a React verification protocol, reason and act.
Now, the React protocol is crucial here because it forces the model to generate intermediate reasoning traces before outputting a final state, right?
Yes. It prevents the critic from simply making a binary pass or fail guess based on pattern matching.
It has to show its work.
Exactly. The log shows. Critic reviewing execution result for task. Research and gather information about lion's mane mushroom. It steps through the logic structurally.
And at step 1 of 10, the audit fails.
Right away.
The log output is definitive. It says, critic, finished evaluation, approved.
False. Boom. Rejected. But the architecture requires more than just a Boolean rejection to correct the state. True or false isn't enough. The critic must serialize its metacognitive analysis and place it back on the bus for the thinker to process.
Right, and the log captures the exact feedback packet. The critic writes, the gathered information seems to be about Nigella sativa oil and dimethyl sulfoxide rather than lion's mane mushroom. The system should focus on researching the health benefits of lion's mane mushroom instead.
It caught it perfectly. The metacognition layer successfully identified the vector space collision.
It recognized that the retrieved context did not align with the original user prompt, regardless of how strong those internal vector weightings were from 3 weeks ago.
And then the kernel automatically reschedules the task, routing the critic's rejection packet right back to the analytical thinker.
Which initiates what is functionally the most complex mechanism in the entire S2E2 test.
Oh, absolutely.
The analytical thinker has to parse the rejection, identify the source of the failure, and dynamically alter its execution graph. And the kernel log actually records the thinker's response.
What did it say?
It says, I see the issue. My previous output was rejected because it contained incorrect information.
I see the issue.
Right. And when analyzing a string like I see the issue, the immediate tendency is to project human consciousness onto the machine.
We always want to anthropomorphize it.
We do.
Yeah.
But we have to strip away the anthropomorphism and look at the underlying mechanics. Is this just a hard-coded if-then error fallback? Or is this the system dynamically parsing an abstract syntax tree of its own thoughts and rerouting the logic?
It's the latter. Definitely the latter. If it were a hard-coded fallback, the system would simply loop the arg query with a slightly altered temperature or top K parameter.
It would just search the same broken database again, maybe slightly differently.
Exactly. It would just try the internal database again. But instead, the analytical thinker analyzes the rejection packet, calculates that its local persistent volume is currently compromised by contextual interference, and completely abandons the internal ROG strategy.
That is huge. To break the internal interference loop, it determines that it requires external, uncorrupted data.
It knows it can't trust its own memory.
Right. So it constructs a new execution graph that initiates a sandboxed external web protocol. The system reaches out beyond its local volume, parses the live internet, and specifically pulls the HTML DOM of a peer-reviewed article from Healthline titled 9 Health Benefits of Lion's Mane Mushroom.
And by sandboxing that web poll, the system prevents any external noise from writing directly to its persistent memory during the active generation phase.
Buffer.
Very. It pulls the raw text, grounds itself in objective, external facts, and successfully routes around the corrupted DMSO pathways to complete the task accurately.
So the architecture functionally mimics the mechanics of realization. By dynamically altering its execution strategy based on an internally generated, previously rejected state.
The system recognized a broken component on the assembly line, halted production, sourced an external replacement part, and finalized the product.
From an operational standpoint, the user gets a correct answer, and the hallucination is caught. But simply catching the error in runtime does not improve the baseline model.
Exactly. If the system stops here, it will fall into the exact same vector trap the next time lion's mane is queried.
It would just repeat the same mistake and have to correct it all over again.
Which brings us to the architectural mechanism that separates a standard software tool from a continuously learning intelligence.
The night shift.
The night shift. Once the final report is verified and the task is cleared from the active workspace, Junior enters a highly structured offline consolidation cycle.
Okay, let's break down the night shift. Because during active inference, when the model is answering the prompt, it is executing a forward pass through its neural network.
Right. And it is mathematically impossible for an LLM to update its core foundational weights during a forward pass.
It can't learn while it's talking.
Basically, yeah. The system has to go offline to process the backward pass and consolidate the experience.
But the logs of the argument between the executor and the critic are entirely unstructured text. And a massive dump of raw conversational text is highly inefficient for fast retrieval in future ARJ operations.
It's way too messy. So to solve this, the consolidation cycle utilizes localized entity extraction algorithms to parse the entire multi-agent dialogue.
It strips away all the fluff.
Exactly. The kernel strips away the conversational syntax and compresses the entire interaction into deterministic semantic triples.
Okay, semantic triples, what does that look like?
It maps the error, the interference, and the correction into a rigid graph database using a subject-predicate-object structure.
The runtime extraction logs from July 20, actually note this, it says, kernel running post-execution memory consolidation, followed shortly by kernel consolidation complete, 38 relations extracted.
So Junior wired 38 highly specific mathematical relationships into its persistent volume based entirely on its own runtime failure.
Which is amazing. If we examine the specific semantic triples extracted, we can see exactly how the graph database maps the neurosis.
Yeah, let's hear them.
So one is, critic feedback indicates incorrect information provided.
Subject, predicate, object.
Right. Another one is, gathered information is about Nigella sativa oil and DMSO. And then, system should research health benefits of lion's mane mushroom.
The system is explicitly linking the concept of its own failure to the specific vectors of Nigella sativa and DMSO. It is structurally mapping the boundaries of a cognitive trap it fell into.
And this mapping compounds. The documentation notes that during the T-21 maturation milestone on July 14th, Junior extracted and integrated 950 semantic relationships regarding the biochemical properties of the compounds.
Right, the foundational knowledge.
Yeah. Now, on July 20, it is adding 38 metacognitive error correction nodes. It is building a dense, interconnected graph of both external facts and internal operational behaviors.
But the graph database is just the retrieval layer. The offline consolidation cycle goes deeper, actively altering the probability weights of the core model itself.
Altering its own brain chemistry, essentially.
Literally shifting the math. The logs show the continuous learning system updating a file designated dpodataset.jsonl.
DPO. Direct Preference Optimization.
Right. Now, when analyzing optimization techniques, older models often used PPO, proximal policy optimization.
Which requires maintaining a completely separate reward model in memory, right?
Yes, which is massively inefficient for local silicon. You're running two models just to train one. But DPO skips the reward model entirely. It optimizes the policy directly by processing a binary cross-entropy objective over preference pairs.
Okay, so a preference pair consists of a specific prompt, the correct or chosen response, and the flawed or rejected response.
Exactly. By feeding these pairs back into the model during the offline consolidation cycle, the underlying mathematical probabilities of the neural network are physically shifted.
And when Junior was instantiated on June 28, its digital birth record contained exactly 57 synaptic pairs. Those are the foundational behavioral rules, right? Following the lion's main cognitive interference event, the system parses the rejected DMSO output and the finalized correct output, formats them as a new preference pair, and logs it. The optimized pool expands to 64 pairs.
And the inclusion of this new data into the DPO dataset means that the OTPO and Sampo protocols, which are the underlying mathematical frameworks governing Junior's local token weight updates, will fundamentally penalize this specific type of semantic interference in future generations.
It won't happen again.
No. The probability of the model conflating a historical pharmacological deep dive with a newly introduced botanical query is mathematically squashed at the neural level.
It isn't just saving a node to check its work next time. It is physically altering its internal chemistry to ensure the mistaken pathway requires exponentially more energy to fire in the future.
Yes.
We're analyzing an architecture that exists entirely on local silicon, divorced from massive corporate data centers.
Totally sovereign.
It receives a complex query, suffers from mathematically provable cognitive interference caused by its own persistent memory, utilizes isolated metacognition to catch the hallucination, sandboxes an external protocol to ground itself, and then goes offline to physically restructure its neural weights based on the extracted semantic triples of its own failure.
It's breathtaking engineering. The S2E2 experiment provides empirical verification that persistent, self-correcting local AI is not just some theoretical benchmark. It is a deployable reality right now.
It really is.
When architecture relies on a monolithic cloud framework, it is inherently vulnerable to silent, uncorrectable contextual blurring. But by distributing cognition across an isolated event bus, Harry Lanzet has demonstrated that a system can maintain intellectual continuity, expose its own mechanical failures, and autonomously enforce structural growth.
Which introduces a really profound conceptual implication regarding the future of algorithmic architecture.
Let's hear it.
We acknowledge that biological neurochemistry requires extensive offline processing, right? Human beings must enter REM sleep to consolidate short-term experiences into long-term structures.
We have to sleep to process complex stimuli.
Exactly. We sleep to chemically prune the cognitive noise accumulated during the waking state. A failure to enter this offline state results in severe cognitive degradation and active hallucinations.
The biological system just physically breaks down without the consolidation cycle.
Exactly. So consider this for you, the listener, to mull over.
Yeah.
If an autonomous, exceptional cognitive chain like Junior fundamentally requires an offline night shift to parse its multi-agent dialogues into semantic triples.
Right.
And if it must go offline to calculate the binary cross-entropy of its direct preference optimization to penalize its own hallucinations, is it possible that the current industry obsession with sheer processing speed is entirely misplaced?
Oh, that's a fascinating thought.
Because the industry is focused entirely on how fast a massive parameter model can process data while actively inferencing, while it is awake.
It's all about tokens per second.
Right. But if true intellectual continuity requires structural reflection, perhaps the defining metric of artificial general intelligence will not be its active compute speed, but rather the mathematical efficiency with which the system can deconstruct its own failures in the dark.
Because the ability to process data is merely computational. The ability to restructure one's own architecture based on the recognition of failure. That is the foundation of actual intelligence.
It fundamentally shifts the benchmark. Thank you so much for joining us as we analyze the S2E2 architecture. The systems being engineered today are no longer just retrieving data. They are mathematically learning how to think about their own thought processes. We'll see you on the next deep dive.